Right, so in the last lecture we had a look at what makes a reaction constant small, and there were three cases where the reaction constant could be small. The first was if the reaction center was far from the probe. The second was if there was both a loss and a gain of electrons in the rate determining step. And the third case was when you had an equilibrium that was preceded by loss of electrons being followed by a rate determining step where there's a gain of electrons or vice versa. And all of these can lead to a situation where the reaction constant, where the gradient of the Hammett plot is very small. Now, in this session I'd like to look at something quite different, and in certain reactions, when you're trying to explore certain reactions, we find that the plot is not linear over the full range of electron donating, electron withdrawing substituents. So, as the first case, we're going to have a look at the acidity of phenoxide anions of phenols, substituted phenols, and we're going to compare that, of course, to our standard reference reaction, which is, of course, the acidity of benzoic acid, substitute benzoic acids. Now, it's interesting to note that for the range of substituents, we get a linear Hammett plot, but in the case of very highly electron withdrawing substituents that are placed in the para position, we find that the points are not on the graph and they're above the graph, as seen over here. So the question we have here is, why on earth would the phenol be far more acidic for the paracyano and paranitro substituted phenols than expected as compared with our reference reaction? And it's fairly straightforward. So a nice example to look at is the paranitro group, and when we draw the paranitro group, please always with N plus O minus, when you draw the paranitro group, you find that the phenoxide anion can speak directly with that paranitro group in terms of conjugation, and the arrows work beautifully, going all the way through, right the way through to the oxygen of the nitro group. And so you end up with another resonance form of the paranitro phenoxide as seen over there. And of course, when the more forms you've got, the more stable that system is. So the paranitro group really stabilizes phenoxide anion, and so that acidity is going to be quite high. But why is it high compared to our reference reaction? Well, look at the reference reaction. Yes, we could draw the arrow coming to the oxygen, we could draw this double bond coming to the nitrogen, and so on, but there's nothing from the reaction center to complete the bonds. So there's no resonance stabilized this is not resonance stabilized. So this system, the phenoxide system, is going to be far more stabilized by the paranitro than the paranitro benzoic acid. And so due to this through conjugation electron withdrawing, we find that these points are not on the line, because through conjugation electron withdrawing happens on the y-axis, it does not happen on the x-axis. So the problem is, what do we do? And the thing is that our standard is not correct for this particular case. If through conjugation electron withdrawing is possible through to a reaction center, we've got to use a different standard. And to get a straight line, we, instead of using sigma values, use sigma minus values. And when you plot it, the sigma minus values take into account the through conjugation electron withdrawing, and so where that happens, you will get a straight line. And of course, we're not plotting log kx over kh against rho sigma this time, but the reaction constant is now called rho minus, and of course the set of values we use are the sigma minus substituent parameters. Okay. It's not surprising that this also happens in the electron donation case, you can see over here that along the electron withdrawing side of a graph, it's perfectly linear, but when you get to the electron donation case, you find that this particular reaction is far more reactive than expected. And if you look carefully at this reaction, it's an SN1 type reaction, and the question is, why would it be accelerated by a para-electron donating group? So when X is electron donating in the para position, why do we see the rate, or the why do we see this far more reactive than expected? And a good choice to show the mechanism of this is to put a para-electron donating substituent in, like the paramethoxy group in, and you can see that the paramethoxy can supply electrons right through to the reaction center, and so we've got resonance stabilized form. So this electron donating group stabilizes it. So the methoxy group is electron donating through conjugation. Okay. Now, of course, methyl group is an electron donating group, and of course we can see how a methyl group can also be electron donating through the pi system, because if you've got a sigma bond that's in line with the pi system, it can donate electron density through the pi system right the way through to the reaction center, and that's called hyperconjugation. So the methyl group is not only pushing inductively through sigma bonds, but of course it's electron donating through the pi system as well, and so we have this system is far more reactive than expected when you compare to our reference reaction. And so in these cases where through conjugation electron donation right the way through to the reaction center is possible, then you're not going to get a straight line with sigma values. And so what we've got to do is we've got to use a new set of standards, the sigma plus Hammett substituent parameters, and of course the gradient will get a straight line, we'll get a gradient as before, but we'll get a straight line only using these values. Please note that we interpret the graphs in exactly the same manner. So if it is has a negative slope, then we know that electron donating groups accelerate the reaction and electron withdrawing groups slow it down, and it's because there's movement of electrons away from the probe, away from the aromatic system, and so forth. And so when you look at tables, and we've seen this table before with our sigma Hammett substitution parameters for the para position, Hammett substitution parameters for the meta position, and of course now the sigma minus and sigma pluses are only for the para position. So you can see over here that we have for electron donating substituents we have got we've got different sigma pluses that are quite different to the para substitute. There's quite a difference between them. You can see they are much higher in value due to through conjugation electron donating. And similarly, take the paranitro group, you can see, compare it to paranitro where through conjugation is not possible. You can see that the through conjugation has changed that Hammett substitution substituent parameter quite a bit. Okay, now just a final point, that in some reactions you will find that using the sigma values gives you a straight line, and other reactions you'll find that using the sigma plus gives you a straight line. But in practice what's happened, what's noticed is that these two situations are extremes. You may find there's some reactions that are not quite at one or other extremes, and so neither of these will give a straight line, and so that gives rise to the Yukawa-Tsuno equation. So the way to understand the Yukawa-Tsuno equation is first to notice that there are sigma, the substituent parameters are normal sigma Hammett substituent parameters, and you can see it appears twice. And then you've got the sigma plus, and or you could put a sigma minus here instead. So how it works is that R, this R is a measure of through conjugation, and that R value can go between 0 and 1. So the way to understand this equation is to first of all see what happens if you put 0 into this equation. If you put R as 0 into this, you can see that all of this falls away, and you get log kx over kh as rho sigma. That's our Hammett equation that we started with. If R is 1, then it's interesting, because then this sigma x cancels with the minus sigma x, leaving rho sigma plus. So that's only sigma pluses. So when R is 0, we've got our rho sigma. When R is 1, we've got our rho sigma plus. And if it's in between, we've got something in between. And so the Yukawa-Tsuno equation can be used in cases that don't quite match either the rho sigma or rho sigma plus as we had. Similarly, don't forget that the Yukawa-Tsuno also works with sigma minuses.